Good morning, everybody. This is Jesse Crawford with Tarleton State University, and this is going to be our first video for the Foundations of Mathematics course for Chapter 3, which covers counting and relations. And the first topic in this chapter is Section 14 on relations. I think a good way to motivate this topic is to think of some of the ways that you've encountered relations in your previous mathematics courses. And there's broadly two ways. The first way is the idea that a relation is kind of like a mathematical operator that connects to objects. So, for example, we might say that a real number x is equal to a real number y. So these two real numbers x and y are related by the relation of equality. Or we might say that x is less than y, in which case x and y are related by the less than operation. Or, there's nothing special about real numbers here. We could be talking about integers and say that an integer x divides an integer y. So this divisibility operator that we've been working with this semester is an example of a relation. We could say that a set A is a subset of a set B. That would be an example of a relation. Or we could even say something totally out there like a triangle T1 is congruent to a triangle T2. So the congruency concept from trigonometry is a relation. So that's the first way that relations have shown up in your mathematics courses up to this point. Now, there's another way that you've seen relations where you've probably actually used the term relation to talk about it, and that's if you have an equation like x squared plus y squared is equal to 25. And in this situation, we, of course, know what's going to happen. If we plot this, we're going to get a circle with a center at the origin and a radius of 5. And what often happens in a situation like this when you're plotting some curve in two-dimensional space is you want to see if it passes the vertical line test. We can look at this and we can see that it fails the vertical line test because we can, draw a vertical line through this curve that's going to cross in more than one spot. And so therefore we know that this curve does not represent a function. It only is a relation. And so this is another way that you've used the term relation in the past. And, in principle, you can write any equation you want over here, and this is actually going to define a relation. Now, the surprising thing that we're about to see is there is a rigorous mathematical definition that connects all these ideas under a single umbrella to define what a relation is. And that definition is incredibly simple. It is simply that a relation R is a set of ordered pairs. And I think for a starting point, why don't we talk about this last relation here and just show that it's actually very easy to see that this is a set of ordered pairs. So we can say, for example, that R is the set of all x comma y such that x and y are real numbers and x squared plus y squared is equal to 25. So that's actually what this relation R really is as a mathematical object. It's a set. It's a set of ordered pairs where every single component in those ordered pairs are real numbers. And for each ordered pair x comma y, x squared plus y squared is equal to 25. And we can write down some ordered pairs that are in this relation. So for example, we could say that the ordered pair 3 comma 4 is an element of R. I'm just going to say is in R for brevity here. But the order pair 3 comma 4 is an element of R. We could also say that the order pair 3 comma negative 4 is in the relation R. And then there's some, maybe do one more. We say 5 comma 0 is in R. And in each one of these cases, all we have to check is that x squared plus y squared is equal to 25. And in each one of these cases, that is actually true. And of course, there's some situations where we have something that's not in this relation. So for example, the point 1 comma 1 is not in R. Now, if we go back to our plot of this circle, what we're really seeing is that every one of these ordered pairs that's in R is really just one of these ordered pairs that's highlighted in red that constitute the graph of this relation. So mathematically, a relation is its graph. The set of ordered pairs that you get when you graph a relation actually is what the relation is. And so, for example, 3 comma 4, the ordered pair 3 comma 4 is up here on this graph. The ordered pair 3 comma negative 4 is down here. 5 comma 0 is over here. But like the ordered pair 1 comma 1 is here in the center. And of course, this is a circle. It's interior to it. Now, as we move forward and talk about relations, it's going to be a bit cumbersome to write things like 3 comma 4s in R. We don't really want to spend a lot of time writing stuff down like that. So instead, we're going to write 3R4. So if we write 3R4, it means that 3 is related to 4 by this relation, which is equivalent to saying that the ordered pair 3 comma 4 is in R. Or similarly down here, we could say that 3 is related to negative 4, or 5 is related to 0. Now, to say that two things are not related, we can actually we can say here that 1 is not related to 1. There's a really nice notation for this that I have in the slides here, and we'll come back to this slide in a second, but you can see here in the slides I'm writing that x is related to x, or x is related to y. But if we wanted to say that two things are not related, we can write it as x not r x, right? So we can just put a slash through that r, and that's going to indicate that those two objects are not related. So yeah, the definition of a relation is really just a set of ordered pairs. That's what a relation is. And I think we've made a pretty convincing argument that this relation right here really is a set of ordered pairs. But what about the examples up here, like x equals y, x less than y, and so on? And the thing is, those actually are sets of ordered pairs as well. So for example, if we're talking about equality, the idea that x is equal to y, what that relation is the relation R. Let me write it this way. The relation equals is simply the set of all ordered pairs x comma y. And again, let's just say we're talking about real numbers here, such that x and y are real and x equals y. Okay, so that's really what that relation is. The relation of equality is the set of all ordered pairs with that property. So for example, 3 comma 3 is in the relation equals. Or we could say that 5 comma 5 is in the relation equals. But again, we don't want to go through the cumbersome process of writing it in this way. So what did we do earlier? We put 3R3, but we don't need to say R because our relation is equality, so we put 3 equals 3. And suddenly, this is the notation that we use all the time, or we can say 5 equals 5. 5 equals 5. And we could say that, for example, 2 comma 7 is not in the relation equality, and therefore 2 is not equal to 7, right? Or, maybe we could write it like this or something, right? Like we do in computer science. So the relation of equality actually is a set of ordered pairs, and it works very fluidly with the setup that we've already shown here. Or we could just do one more quick example. Let's talk about less than. So less than, we're looking at x less than y. So the less than relation is the set of ordered pairs x comma y, such that, and again, let's say we're talking about real numbers right now, x and y are real and x is less than y. So we would say, for example, 2 comma 5 is in the less than relation. But again, we can simply say 2 less than 5, right? That's a more efficient way to write that. Or we would say something like, 5 comma 2 is not in the less than operation. And so that would be summarized by saying 5 is not less than 2. And so, when we're writing this out by hand, we can put a less than sign with a little slash through it. So yeah, every relation that you've encountered in your mathematical career up to this point is really just a set of ordered pairs. But you might be wondering right now, you might be saying, is this really true that just any old set of ordered pairs constitutes a relation? I mean, what if we put something like R is the set, and let's just jot down some ordered pairs here, like 1, 2, 1, 3, and maybe another ordered pair. Let's look at 3, 0. And this is a set of ordered pairs. Is this really a relation? And the answer is yeah, that's a relation. By definition, a relation R is simply a set of ordered pairs. And we should point out that we can actually graph this relation. So in the same way that we can graph the relation of a circle, we can graph this relation, and it's not as interesting. It's not like this is a mathematically really interesting relation to consider, but this set of ordered pairs, we can just graph it in this way, and we get these three ordered pairs, right? We get 1, 2, 1, 3, and 3, 0. And then we could write things down like, 1 is related to 2, and 1 is related to 3, and 3 is related to 0. Note, by the way, that the reason that 1 is related to 2 is, again, because the ordered pair 1 comma 2 is in R. That's what it means for 1 to be related to 2. But I want to point out that the ordered pair 2 comma 1 is not in R. And what that means is that 2 is not related to 1. And so this is a really important idea. It's not necessarily the case that if x is related to y, it does not necessarily follow that y is related to x. It may not be, right? Like this is an example of it. And another example would be the one that we looked at earlier. We looked at something like 2 is less than 5, but 5 is not less than 2. And so in a minute, we're going to go to the next slide and we're going to talk about some of the properties that relations have. If it is true that whenever x is related to y, that y is related to x, that's called a symmetric relation. But it could also be the case that that's not true. And so we'll come back to this in a second and look at all of these properties. Before doing that, though, we need to really shore up this definition and make sure we're really clear on how this works. So according to this definition, a relation R is a set of ordered pairs. Now, underneath this, it says let A and B be sets. We say R is a relation from A to B if R is a subset of A cross B. Now, as a quick reminder here, if A and B are sets, then A cross B is the Cartesian product of A and B, and this is the set of all ordered pairs A comma B such that A is in A and B is in B. So this is the Cartesian product of A and B. And the first thing that we should point out is that if R is a subset of A cross B, then R really is a relation. And there's a really easy way to see this. If R is a subset of A cross B, then every element of R is an element of A cross B. But if we have an element of A cross B, it has to be an ordered pair. So that would mean that every element of R is an ordered pair, but that means R is a set of ordered pairs, and so it is a relation. So first of all, it's clear that if R is a subset of A cross B, then R is a relation. On the other hand, if R is a relation, it's a set of ordered pairs, and the elements of those ordered pairs have to live somewhere. Let's just say that all of the elements in the first component live in a set A, and all of the elements in the second component live in a set B. Well, then that relation R consists of ordered pairs that are inside of the Cartesian product of A and B. So this definition here is actually completely equivalent to the first definition. A relation is simply a set of ordered pairs, but that's equivalent to saying that R is a subset of A cross B for some sets A and B. And when this happens, when R is a subset of A cross B, we say that R is a relation from A to B. And this is very similar to whenever we say something like f is a function from the reals to, let's say, bracket 0 comma infinity, right? So an example of this would be if I have f of x is equal to x squared. That is a function that maps the reals to the interval from 0 to infinity, right? So in the same way that we want to talk about a function going from a domain to a codomain, we want to be able to talk about a relation having a domain and a codomain. If you haven't heard the term codomain before, don't worry about it. We're going to cover that later. And actually in a later section, we're going to talk about how the concept of functions is actually intimately connected with this concept of relations. But yeah, we want to be able to deal with this. Now, a situation that occurs very frequently is that the set A and the set B that we have in our relation are just the same set. In fact, all the examples we've talked about today have that property. So like when we were talking about the relation x equals y, we were talking about real numbers. So the domain and the codomain of that relation were both real numbers. Or when we talked about x less than y, we were talking about real numbers. When we were talking about x divides y, we were talking about integers. So usually what happens very frequently is this set and this set are the same, And if that's true, then really R is a subset of A cross A, where A is basically like a universe that this relation is defined on. It's like a domain. It's some set where this relation is defined. And so in that case, we would just, instead of saying that R is a relation from A to A, we would just say R is a relation on A. That's how we would write that. Okay, now before going on to the next slide, there is a concept down here that's interesting. It talks about if R is a relation, we define the inverse of R, which is written as R inverse, as the relation formed by reversing the order of all ordered pairs in R. So, and you can see the definition is here. R inverse is the set of all xy such that y comma x is an element of R. And I think a really good illustration of this is if we talk about the relation less than, and we can talk about what its inverse is. So the relation less than is the set of ordered pairs x comma y such that, let's just say x and y are real and x is less than y. So that's what that relation is, right? So let's actually talk about what the inverse of this relation is. So we can say the inverse of, and actually I'll write it this way. I'm going to take the relation less than, and I'm going to compute its inverse, right? So it's a bit awkward to write it that way, but that's actually what we're talking about here. So we have the relation less than, and we're going to take its inverse, and that's simply going to be the set of all ordered pairs x comma y such that, and let's think about what is the definition of inverse. So x comma y is in the inverse of a relation if y comma x is in the original relation, right? But we actually know what it means to say that y comma x is in the less than relation. It would mean that y is less than x, right? So now on the next line, we can say that this is equivalent to the set of all x comma y such that, and so again, what we're saying is y comma x is in the less than relation if and only if y is strictly less than x. That's what that would mean. But we could also, if we want to, we could rewrite this as saying this is the set of all x comma y such that x is greater than y. And suddenly what we realize is that the inverse of the less than relation is the greater than relation. So this is just the greater than relation. So this is actually a really natural result. This is really intuitive. If we take the less than relation and we take its inverse, what we're doing is we're taking all of those ordered pairs and switching them, and this results in the greater than relation, and that's actually really intuitive and quite natural. Again, if we have a function f, we can sometimes talk about that function's inverse. Of course, not every function has an inverse, but sometimes they do, and it turns out the notion of the inverse of a function is actually going to be highly related to this. So we'll come back to this later. Okay, so now we want to talk about properties that relations can have, and we have 5 properties here, and we're just going to go through and look at these properties, and we'll do a couple of examples. We'll talk about which of these properties are satisfied by the equality relation and which of these are satisfied by the less than or equal to relation. Now, before we can even talk about a relation, we do need to have some set A that relation is defined on. So in this context, we're saying let R be a relation defined on a set A. So again, A is kind of like the universe that you're living in. And like in this example, let's just say that A is the real numbers, okay? And we're going to talk about the relation equals and the relation less than or equals. And we might actually just run through these real quick and talk about each one of these and sort of why these are named what they're named. So this first one says, if it's true that for every x in your universe A that x is related to itself, then we say that the relation is reflexive. This is pretty reasonable, right? It's like if you look in the mirror, you're going to see a picture of yourself. So you're going to see a reflection of yourself in the mirror. So if x always sees its reflection on the other side, then R is a reflexive relation. If x never is related to itself, then it's irreflexive, which is a very reasonable term. This third property that says, if it's always true that if x is related to y, then y is also related to x, then R is symmetric. So if you're related in one direction, you're always related to the other direction. If that condition holds, it's a symmetric relation. And this is, again, a very, very reasonable term. Symmetry means that something is the same on both sides. So if the relation is true written in this direction, if it's always true written in the other direction, there's kind of a symmetry there. It's a symmetric relation in that sense. This fourth condition of anti-symmetry, this is a rather complicated condition to hold. Let's see what this is saying. If for every x and y in A, if x is related to y and y is related to x, that implies that x is equal to y. We call R antisymmetric. This one might be a bit hard to think about right now, but I think it'll be a lot more clear once we go through these examples in a second. So we'll come back to this in a minute. And then the last one here is something that you guys have all talked about a lot in your previous math courses. You speak of things like the transitive property of equality or the transitive property of less than, stuff like that. And what that is saying is if you have three elements, x, y, and z, and for any x, y, and z in your universe A, if x is related to y and y is related to z, then x is related to z. And there's a lot of relations that have this property, and this is called the transitive property. So let's just run through these real quick, and let's example one. Let's talk about equality, and let's just write down what these would be for each of these properties. So our first property here, we would say, is it true that for all x, and again, for right now, guys, let's just assume we're talking about real numbers. So I'm not going to write that out every time. I'll just say for all x here. So for all real numbers x, is it true that x is equal to x? And the answer is, yeah, that's true, right? So again, the equality relation is this relation equals. And what this condition is saying is it always true that for every x in your universe that x is related to itself? Well, in the case of equality, that would mean for all x in the real numbers, is x equal to x? And the answer is, yeah, that's true, right? It's always true that everything's equal to itself. So that is a reflexive operation. Is it true that for all x, that x is not equal to itself? And of course, that's certainly false. That just can't ever happen. So equality is not an irreflexive operation. What about for all x comma y, is it true that if x is equal to y and, is it true that if x is equal to y, then y is equal to x? Is that true? And the answer is, yeah, that's true, right? So if two things are equal in one direction, if you switch the order, they're still equal. And so the equals relation, the equality relation, is symmetric. Part D. Let's write this one out. So this one would be for all x comma y, if x equals y and y equals x, then x equals y. This one is a bit trivial in this case. This one actually doesn't make a lot of sense in this situation, but it is a true statement, right? If both of these conditions hold, well, then in particular the one on the left holds, but the one on the left says that x is equal to y, so yeah, it is true that x is equal to y. So this is true, and so the equality relation is antisymmetric, but some of you might be saying, but it's symmetric, so how can it be antisymmetric? And these terms do allow for the possibility that a relation can be symmetric and antisymmetric. It's not something that we're going to talk about a lot, but that actually can happen. And I think this will be a lot more clear after we go through the less than or equal to example. Okay, our last example here for equality, is it true that for all x, y, and z, if x equals y and y equals z, then x equals z? And of course that is true, right? So if you have three numbers and the first two are equal and the second pair are equal, then all three of them are actually equal. So the equality relation is a transitive relation. And I'm sure you have spoken about this in your algebra classes before, the transitive property of equality. All right, well, let's go through and talk about, well, actually, before we talk about less than or equal to, I want to point out a few things real quick. The equality relation, there's 5 properties up here, but I really want to focus on 3 of them. So the equality relation is reflexive, symmetric, and transitive. And it turns out that any relation that has these three properties is called an equivalence relation. And the way you want to think of an equivalence relation, we're going to study this in depth in a subsequent section in the course. But an equivalence relation is simply a relation that says that two things are either equal or they're in some sense equivalent. Like a really good example of it would be, we talked about triangles being congruent earlier. Is the relation of congruency, is it an equivalence relation? And the answer is yes, because we just have to check three things. Is it reflexive? Is it symmetric? And is it transitive? So is it true that for every triangle, it's congruent to itself? Yes. Is it true that for any two triangles, if x is congruent to y, then y is congruent to x? Yes, that's true. Is it true that if you have three triangles and x is congruent to y and y is congruent to z, then x is congruent to z? And yes, that is also true. So an equivalence relation is basically a relation defined on some space that kind of says that the things in that space are equivalent in some sense. Now let's move on to the less than or equal to operation and talk about its properties. So we'll talk about the less than or equal to relation. And so let's go through each one of these. Is it true that for all x, that x is less than or equal to x? And the answer is yes, that is true. Every element is less than or equal to itself. Part B, is it true that for all x, x is not less than or equal to x? And the answer is that is not true. And you know, this is actually the second example we've done here where the relation is not irreflexive. You know, it might be helpful to do a third example real quick. Example 3, let's just talk about less than, right? And we'll just do part B for this one. Is it true that for all x, that x is not less than x? And the answer is yeah, that's true, right? A real number can never be less than itself. So the less than operator would actually be an example of a relation that is irreflexive. But yeah, we'll sort of set that aside here. Okay, let's go back to example 2. We're talking about less than or equal to. Part C. Is it true that for all x comma y in the real numbers, that if x is less than or equal to y, then y is less than or equal to x? And the answer to this is that's actually false, right? That's actually not true. And a good example of it would be, 3 is less than or equal to 5, but 5 is not less than or equal to 3. And, this really captures the idea that symmetry should really mean that the relation is the same when you flip it, when you reverse the order. So the equality relation is symmetric because if you reverse the order of equality, it's exactly the same operation. But if you reverse the equality of less than or equal to, you're going to get greater than or equal to. You're actually going to get a different relation in that way. So yeah, this is actually not a symmetrical operation. All right, part D, let's see if it's antisymmetric. So for all x comma y, is it true that if x is less than or equal to y and y is less than or equal to z, or y is less than or equal to x, then x is equal to y? So yeah, let's think about this for a second. So we're dealing with two real numbers. We're dealing with two real numbers here with the property that x is less than or equal to y and y is less than or equal to x. Is it true then that those two numbers are equal to each other? So they actually would have to be equal, right? Because if x was strictly less than y, if y was actually a bigger number than x, well then it would not be possible for y to also be less than or equal to x. The only way that x can be less than or equal to y and y can be less than or equal to x is if they're actually equal to each other. So this is actually a true condition. So from part C, we saw part C was false. That shows that less than or equal to is not symmetric, right? The less than or equal to operation is not symmetric, but according to part D, it is antisymmetric. And hopefully this example really helps to clarify what antisymmetric, the purpose of this, this concept here. It's basically saying that in some sense, the only way that you can get this symmetry is when the two elements are actually equal to each other. And so in this sense, this is kind of what this concept of antisymmetry is trying to convey. Last example here, part E, we're going to see if this is transitive. So is it true that for all x, y, and z, if x is less than or equal to y, and y is less than or equal to z, then x is less than or equal to z. And of course, this is also true. And basically, a good example of this would be something like, 3 is less than or equal to 5, and 5 is less than or equal to 7, then we are going to have that 3 is less than or equal to 7. So it's kind of like you have a small number that is less than or equal to a medium number. The medium number is less than or equal to the large number. Then that first small number would be less than or equal to the large number. So this is actually a true statement as well. Now, when we talked about equality, I mentioned that equality has the property that it is reflexive, symmetric, and transitive, and any relation having these three properties is called an equivalence relation. So on this one, let's focus in on some of the properties that this less than or equal to relationship has. And three of the properties it has that are really interesting are less than or equal to is reflexive, antisymmetric, and transitive. And any relation that has these properties is called a partial ordering. So an equivalence relation is a relation like congruency between triangles that says that one thing is kind of equivalent to another thing. An ordering is a relation that says in some sense that one thing is less than or equal to something else. Now, of course, less than or equal to is an operator that says a number is smaller than or equal to another number. And the reason you say that this is an ordering is because it allows you to order the elements of your set. Like if you think of the real number line, you've got all these points on the number line and they're placed in an order. Like, 1 is less than or equal to 2, which is less than or equal to 3, which is less than or equal to 4. And so this operation of less than or equal to allows us to place all of the real numbers into an ordering. And you might wonder, why is the term partial being used here? It turns out that there are certain orderings that are only partial orderings. They're not total orderings because they don't actually compare every single pair of possible points in the set. Now, for these examples here, we're talking about real numbers. This actually is a total ordering. So it is true that for any two real numbers, you can compare them. And in that sense, it is a complete total ordering. There are partial orderings, though, that are not total orderings. Let's just look at a really quick example and we'll call it a day. So an example of something that is a partial ordering that is not a total ordering is the subset relation. So let's talk about subset real quick. And we'll just look at three things. We'll just check, is it actually reflexive? Is it antisymmetric? And is it transitive? So is it true that for any set A, that A is a subset of A? And that's true. That's actually a true statement, right? So that means the subset relation is reflexive. Is it true that for any A and B, that if A is a subset of B and B is a subset of A, then A equals B? And that's actually true, right? In fact, that's the definition of equality of subsets. If A is a subset of B and B is a subset of A, then A is equal to B. So that is also a true statement. And so what we have so far is that the subset operation is reflexive, and what this shows is that it's antisymmetric. And then last, we can say for all A, B, and C, if A is a subset of B and B is a subset of C, then A is a subset of C, and that is also true, right? So you can kind of draw a Venn diagram to show this. If A is completely contained in B and B is completely contained in C, then the original set A would be completely contained in C. And we could also write a formal proof for this, right? I think you guys have even written one of these proofs in a previous homework assignment. So again, this tells us that subset is reflexive. The second condition says that it's an antisymmetric relation, and this third condition says that it is a transitive relation. And therefore, subset is reflexive, antisymmetric, and transitive. And therefore, the subset relation is a partial ordering. Now the question is, why is it not a total ordering? And the reason is because you can simply have two subsets where neither one is a subset of another one. So for example, I could define A to be 1, 2, 3, and we could define B to be, maybe 1, 1, 5, 7 or something like that, right? And in this case, A is not a subset of B and B is not a subset of A. So this ordering is not a total ordering in the sense that it doesn't completely order all of the elements under consideration. It will order some elements, but it won't order other elements. And this is why this term of partial ordering exists. Well, anyway, guys, we've been going for a while now, and I think that's probably a good place to stop for this section. As always, these are the homework assignments. You can see that the ones to discuss are here, and hope you all benefited from this. If you have any questions about this at all, any comments on how to improve or things you liked or things you didn't like, feel free to let me know. This semester, you can contact me by email. You can also post a question in the homework and lecture help form in Canvas. But basically just reach out to me. I'll also be conducting some office hours via Zoom. So just let me know what you think, and I'll see you next time.